Hi there. During this session I'm going to be talking about thermodynamics. The definition I have here is the name given to the study of processes in which thermal energy is transferred as heat and as work. Now we should already recognize that heat is the process of energy transfer as a result of a difference in temperature, and work is a measure of energy transferred. This session is going to be all about the processes. So we're looking at the processes, and all these processes are going to be related to gas and bodies of gas, and how heat and work can have an impact on those. So I'm going to start off by introducing you to the first law of thermodynamics. The first law of thermodynamics says that energy can be neither created nor destroyed, only transferred or transformed. Now, within the context of work and heat transformation, that means if I look at a gas, I know that the heat energy flowing into the gas, so that's the energy being provided to the gas, is going to be transformed into either the change in internal energy of the gas, or is going to be used by the gas to do some work in some way. That could be expansion, so that's an example of work. I'm going to go into that in more detail later on. So this is kind of our starting point, our reinterpretation of the first law of thermodynamics. It should also be noted that this change in work is positive if it's work done by a gas. Later on we're going to see some examples where that's going to be a negative value when we're considering doing work on the gas itself. So if someone is putting effort in to compress the gas, then that would be an example of a negative value for the work done. But the conservation of energy is still valid. So the first one of the examples of processes I'm going to talk about is something called isobaric. So an isobaric change is when gas expands or contracts at a constant pressure. Now commonly we show these changes using a pressure volume graph. So here's my pressure volume graph, and I've got pressure and volume, and I'm saying that the pressure is constant, so that's why we have a horizontal line here, and the volume changes from volume initial to volume final. Now notice that there's an area which is identified as work done. So let me just explain that. What we're going to find out in a second is that our idea about the conservation of energy can be updated in this situation to show that the amount of heat transferred is going to be equal to the change in internal energy plus the pressure times the change in volume. Now that pressure times the change in volume is replacing the work done. So let me explain that. We know that work is force times distance, and can be calculated as. And we know that pressure equals force divided by area. Now that means that pressure times area is equal to force, so work is equal to pressure times area times distance, and that simplifies into pressure times the distance travelled, in this case the change in volume as a whole. Okay. So my work done is equal to the pressure times the change in volume, and that quite simply is the area underneath this line indicating the change in an isobaric process. Okay. So that's just joining the dots there, and we recognize that work done gives us the area underneath this change graph. So there's one process. Isochoric, this is when gas does not expand or contract, so it's in like a sealed container. So in this case my sealed container can get heated up, and by heating up there's a pressure change, but there's no volume change. Now that pressure change is obviously going to be related to the fact that there's a change in temperature. And what I find here is as there's no volume change, there's going to be no work done. All the energy in theory goes directly into the changing of the internal energy. So all the heat going in goes directly to changing the internal energy of the gas. Next term or process I'm talking about is isothermal. This means the gas expands or contracts at a constant temperature. So this means heat needs to flow into or out of the gas to maintain that constant temperature. Now, as we can see here, work done is still going to be the area underneath the line of change. So we've got an initial pressure and volume here, and a final pressure and volume, and that change is shown by the line, and the work done is going to be underneath that line there. So here's a question relating to this. As a gas syringe is free to move, 100 joules of heat is applied to the gas that expands isothermally at atmospheric pressure. By how much does the volume of gas increase? So there's a few things to note here. We recognize that the heat supplied is 100 joules, so my change in Q is 100 joules. Now, since the temperature is constant, the internal energy is going to be unchanged, so that means my change in U is going to be 0. Hence 100 equals 0 plus constant pressure times change in volume. Now notice here it said that it expands isothermally at atmospheric pressure. So that means the pressure itself stays the same all the time, so it becomes a constant in this situation. Therefore, I can do a calculation of the change in volume is going to be 100 divided by, that should be 10 to the 5, and therefore my change in volume is going to be 0.001 meters cubed. Adiabatic is another change, and what happens here, adiabatic means that no heat flows into or out of the gas. Compression makes gas temperature rise, expansion will make the gas temperature cool, okay? But there's no heat flow going in and out. So here we have an adiabatic curve, and see we've gone from one temperature to another temperature, and what we can see here is that this area in red is the work done from that change. Now in this case, if there's no heat flow, that means change in Q is going to be equal to 0, and therefore we recognize that the drop in internal energy is going to be equal to the change or the amount of work done. Here's another question about adiabatic compression. 1 mole of gas at 300 degrees Kelvin is in an insulated syringe, is free to move. So it's insulated, so no heat can go in or out, but it's free to move. 100 joules of work is done on the gas, so remember here work is going to be negative, compressing it adiabatically. By how much does the internal energy of the gas increase? So think through this process. We know from our first law of thermodynamics. Now, we know that the work done is going to be minus 100 joules, and we know that the change in Q is going to be 0 because there's no heat entering or leaving during the compression. This means that my change in internal energy is going to be 100 joules. The gas temperature rises.